Hello viewers, welcome back. In this video lecture we are going to continue the discussion of orientation and reactivity of monosubstituted benzene. So in the last lecture we discussed how the existing functional group or the substituent will decide the orientation and reactivity, and we classified those groups as a ortho-para directors and meta directors. Now next question is arising in our mind, why certain groups specifically can act as ortho-para directors and why not meta directors, vice versa. Okay, in this lecture we took one example in each section category. Here we took OH as a ortho-para director and nitro group as a meta director, and why this group are acting as ortho-para and meta respectively. Okay, now first we start with the ortho-para director, and now the OH group, that monosubstituted benzene have been taken. This electrophile is going to substitute ortho. So this is the resonance structure is formed like this, and now we are going to draw the resonance structure. Okay, now we will get the second resonance, and if you draw another resonance we will get like this. Similarly we are doing for the meta. If the electrophile is substituted at meta, then what will happen? So like this. So this is the way, and like this. So we completed the resonance structures for the meta position also. And next the para. If it is attacking at ortho, electrophile is getting substituted at para. So like this we will get, and we will get the another resonance structure. Okay, so and we have drawn this resonance structures. So this we already discussed in the general aromatic electrophilic substitution reaction mechanism. This, the sequentially rotation of this arrow, you no need to memorize it. Please understand it that you have to rotate it sequentially. Okay, now we completed the ortho-para and meta, the all substitutions at for the OH group. Okay, now we are going to compare the resonance structures of this all ortho, meta and para resonance. As we know, this is the one general rule: if we have more resonance structures, that will be maximum stable. Now just observe the ortho. Now you see here in the first one, just I am putting this is the first resonance structure. You see this we are drawing. Is this another way of this carbocation, the arenium ion can be stabilized by the movement of this lone pair electron. So we will get by another resonance structure like this. For example, I am drawing like this. The oxygen will get positive charge like this, and like this. Like this, one more resonance structure we can get it for the ortho attack, because the lone pair electron on the substituent is this stabilizing the arenium ion. Now let's see for the meta. You see there we don't have any you see the positive charge has been formed at the OH connected carbon. You see there is no positive charge in the three resonance structures of the meta substitution. See, there is nothing. Now come to the para. Now come to the para. You see this one I am drawing. This is as a second resonance structure. You see here also this OH group, the connected carbon is having the positive charge, that can be stabilized by like this, and we can get one more resonance structure like this way. Okay. So like this. Like this you can get it, positive charge. So you are getting one more resonance structure for the ortho and para substitution, and for the meta we don't get any substitution. Okay, any extra resonance structures. That's why this OH group is acting as preferably ortho para directing groups. I hope you will understand it. Now next we see why the nitro is acting as a meta directing groups. You see, in this case we took the nitro as a substituent and we tried to substitute at all positions. Okay, like similarly we discussed. Okay, so we get all the substitutions by this way and this way. So we got the resonance structures for all the case, ortho, meta and para. Okay, by this way. So we got the resonance structures. In the meta substituent, you see the nitro group is having the positive charge and it is an electron withdrawing group, and this cannot stabilize. You see, I am putting this one as a third resonance structure. In the third resonance structure, you see that wherever the nitro group is connected, that carbon is also having the positive charge. So this will destabilize it. Okay, so the third resonance structure will create more destabilization. Similarly, and you see in the para, here also you see wherever the nitro group connected, that carbon is also having a positive charge. Both that the electron withdrawing group is connected to the positive charge carbon, so that will destabilize, so that will create more instability. But if you see in the meta, wherever this positive charge has been away from the electron withdrawing group, that why this will reduce the destabilization. That's why whenever the electron withdrawing group, that is meta directing groups, that will prefer the substitution at meta positions. Okay, so this is the reason. So here this will not create that much instability. Okay, so it will, so this positive charge is away from this electron withdrawing group, that will cause the less destabilization. Okay, so that is the reason these groups prefer whatever the meta directing groups will prefer the substitution at a meta position. Okay, so these are the main reasons. Okay, now ortho para director is giving a para as a major product. Why? What is the reason? That we are going to discuss. The reason is, if we see this one, something is a group, so this will form electrophile, and this is like this. Okay, so this is the para product and this is the major one and this is the minor one. The reason is, here this group will cause some steric hindrance. That's why the para group is, the para substitution is always a major product. Okay, because so this ortho position creates some steric hindrance. That is the reason the para is forming a major product. But theoretically, that is not the correct way. But theoretically, this whatever we are discussing, this is the experimental. But in the theoretical, you see, in this case, here both are ortho position and one is the para position. So total 3 possibilities. So 2 out of 3, that means nearly 66.66% we should form the ortho, and 1/3 is for para, that is 33.33%. But para should form lesser amount theoretically, because it is having only one position. But in the ortho, for ortho we are having 2 positions, so that means this should form in maximum amount, that is ortho product should form in the maximum amount. But in the experimentally, that is not possible, because the reason is here it is a steric hindrance. Okay, so theoretically, how much this is the ratio, around 67 and 33% for the ortho and para. Okay, but experimentally para is forming major due to the steric hindrances, the ortho forming as a minor product. I hope you understand this lecture. So we will see in the next class. If you understand this video lecture, kindly subscribe and share this. Thank you.